So let's recap where we left off last time, which was developing and presenting the criteria for spontaneity. So different processes have different occurrences happening within them. Some of those changes involve heat changes and exchanges, which is what the change in enthalpy measures. Those same processes will also be associated with changes in the relative organization of the particles involved in the process, which then entails a change in entropy. And of course, the temperature will play a significant role in the outcome, because depending on temperature is how everything else ends up happening. So when you take into account those three things together, as long as the magnitude of the change in enthalpy from which you subtract the product of the magnitudes of the absolute temperature at which that process is occurring times the entropy change, as long as that number that comes out is a negative value under those conditions, that process will be spontaneous. Nothing needs to happen. No intervention needs to be done. You just put it together, walk away. It's going to happen on its own. If under the conditions that you're trying to carry out the process, it turns out that delta G is a positive number, then it's not happening spontaneously. In fact, what's spontaneous is the reverse process, because as we already saw with delta H, if in one direction delta H was positive, in the other direction it's going to be negative. So the same thing applies to delta G and delta S. If the reaction going in one direction has a positive delta G, well, in the opposite direction it has a negative delta G, and that then tells you that the reverse process is what's truly going to be happening. Turns out, as we said, reactions ultimately proceed to chemical equilibrium. At that point, because neither direction is technically favored, it can go either way with equal predictability, then that's the moment where we say that delta G is equal to 0. So the main thing you need to get out of this is that the spontaneity of a process is dependent on both the enthalpy and the entropy changes that occur, and then the temperature at which you're trying to carry out that process is what ultimately will also determine the outcome. So let's look at some examples of transformations so that you can sort of start putting this together. We're going to focus on entropy because we've already talked about enthalpy. So when you're looking and trying to establish what is the change in entropy for a transformation, there are two general factors that determine whether that entropy change is positive or negative. Remember, positive entropy means things get disordered. Negative entropy things means get ordered. So first is the relative number of moles of products versus reactants. If you make more moles of products, you make more things from less things, the disorder is increasing. Yes? If you have a piece of some kind of a rock or some kind of a piece of chalk, let's say, and you hammer it, and it breaks into 50 pieces, you've increased the disorder, right? From one thing, you've made more, right? That comes with an increase in the entropy. Conversely, if you're making less from more, in terms of numbers of moles of substances, so there's less products in terms of numbers of moles relative to the reactants, then the reaction is getting ordered in that regard, and that is associated with a decrease in the entropy. So, for example, we intake carbohydrates as part of our diet. Glucose, fructose, galactose, as we're going to learn, all end up having the same formula that we see here, C6H12O6. As part of our metabolism, ultimately it gets metabolized to CO2 and water through the intervention of oxygen. Now, as you see it there, that reaction looks like a simple combustion reaction. And yes, if you take a piece of glucose in the laboratory and stick it under a flame, this is what's going to happen. It's going to undergo combustion. In the human body, it's It's a much more complex process, but that ultimately carries out the same transformation. All carbs that you eat become CO2 and water. Oxygen is consumed in the process, not directly associated with glucose, but as we're going to learn later when we see metabolism, oxygen has a very critical role in this whole process. But the whole point of this discussion is not that. It's that if you observe, there are 7 moles of reactants. There's 12 moles of products. So the breakdown of glucose through its metabolism or oxidation to CO2 and water has a positive delta S because you make many more product particles than you started with in the reactants. We're going to look at another pathway at some point, again, when we talk about metabolism, which involves the elimination of nitrogen. The body cannot store nitrogen. So nitrogen is contained as part of the general structure of proteins. There are other nitrogen-containing compounds, DNA, RNA, and heme, for example, contains nitrogen. So there's all kinds of places where the body uses nitrogen. This is why you need to intake proteins into your body, because the body takes those proteins, breaks them down. Some of those pieces are used to make more proteins within the body. Some of those pieces are used to make all of these other nitrogen-containing compounds. Once the body's done using all of the nitrogen intake, and it's done, any excess must be excreted. We cannot store nitrogen as a depot of nitrogen. We can do that with carbohydrates. We can do that with oxygen is stored within hemoglobin, right? So ultimately, the nitrogen that's in excess gets converted technically to ammonia. It's actually ammonium, but technically to ammonia. And that ammonia will then combine with CO2, and then here is shown as phosphoric acid. In reality, in the bodily fluids, it is these phosphate-type compounds. This is a little bit oversimplified. But anyway, the point is the net reaction is sort of what's shown here. These 3 particles end up producing these 2 particles, right? So from 3 you go to 2, there's been ordering of the process, right? So this is a reaction in which, because you end up with less products at the expense of more reactants, there is a negative delta S in that regard. The second factor that affects entropy is relative number of what we call degrees of freedom. So how free are the atoms in a structure to move around, rotate, move from point A to point B without breaking the structure, obviously. So we're talking about possible conformations, meaning relative three-dimensional arrangements through bond rotation. Whenever that increases, if a structure is initially constrained, it forms some kind of a ring structure, and then that ring opens up and the atoms now can move and rotate around and have more freedom of motion. That comes with an increase in entropy. The exact opposite happens if there's a ring closure or ring formation, in which now the atoms are constrained within the boundaries of a ring framework. That comes with a constraint. The moment you limit things from being free, then that reduces the entropy, right? Because entropy is about randomness and freedom. So here's glucose, for example. We're going to look at these structures a little bit later. Here's glucose drawn in a particular way to illustrate the fact that when glucose is in fact in an aqueous solution, one of the alcohols that's sort of towards the end of the structure, if we consider this aldehyde the first carbon, there's a little bit of a rearrangement over here. This is a rearrangement reaction, right? How do I know this is a rearrangement reaction? It's the same composition, it's just that things have moved around. Same thing on the top, right? This has been an opening of a ring here. Notice how this ring opens up to get this, and then this can actually sort of rotate and extend itself. Now that it's extended itself, it is free to, all those atoms are free to move more freely, for lack of a better word, right? So this is a positive delta S, this whole process. Here, because a ring has formed from an open chain compound, this comes with a negative delta S, okay? So the these examples are chemical transformations. You can also speak of changes in entropy in a physical change. And in that scenario, what is making the difference in entropy is the relative position and or organization of the particles. They haven't changed their identity. They've just changed how they are organized relative to each other. So when particles become separated, they start close to each other, suddenly they become separated, well, that increases the disorder, right? That comes with a positive delta S. Whenever you have an organization of particles, whether they're the same, meaning that it's a pure substance, or some kind of mixture, when they're sort of completely random and they suddenly become organized, then that comes with a decrease in entropy, right? So we sort of saw this previously, but we saw that we were looking at it more in the context of enthalpy, if I recall correctly. Enthalpy, sorry. So here is, again, the melting and vaporization of a substance, right? As the temperature increases, the entropy is progressively increasing because the particles start to move a little bit faster. Then at the melting point, there's a sharp increase in the entropy. Entropy is the y-axis, right? Notice there's a sharp increase in the entropy. Not huge, but significant enough. So now, when you get to the liquid, it has a higher entropy than the solid. And then as you heat the liquid, because the particles progressively are moving faster and faster and faster, temperature, remember, increases kinetic energy, particles. And then once you get to the boiling point, that's when there's a dramatic increase in entropy, because that's when the particles are really far away from each other. Okay? And of course, the converse gives you the negative entropies. If you condense a gas to a liquid, there's a huge loss of entropy as it condenses. And then as the liquid cools down and ultimately crystallizes to form a solid, the entropy is progressively decreasing. Okay? So here's a question. There's two reactions here that have a positive delta S. Based on what we've said and what you see, which two have a positive change in entropy? Okay? All right. And the answers are? So let's dissect it. If you look at A, what happens in A? What's happening? So you're making less particles from more particles. There's two reactants. There's one product, right? So that is a organization. There's less randomness because these two things, 1 and 2, right, come together and they're making 1. That automatically comes with a change in entropy that's negative. That would be an organization, right? For the second one, B on the bottom left, it's 1 to 1, so there's no change there. However, you have a completely open chain compound in which now you have a ring closure. So a new bond is formed between this atom and this atom. This closes the ring, right? So ring closure automatically comes with a negative delta S. That's exactly the opposite of what's happening in C, right? You have a ring that opens up when this bond breaks. So that comes with greater freedom of motion of the atoms in the structure. And then in the case of D, you have one reactant that ultimately breaks apart into 2 pieces as this bond breaks. That comes with a positive entropy. So these two are associated with positive entropy. Okay? All right. So, based on the mathematical definition of delta G, you can make inferences of how temperature affects the spontaneity of a process depending on whether the reaction is endo or exothermic, which is what's on the top, versus getting disordered versus ordered. And all you need to do is, you can do this very qualitatively. Predict what's going to be the sign of this mathematical calculation based on these two, and then what does the temperature have to be in order to make this a negative number, right? Because for spontaneity, that value has to be less than 0, right? Negative. So if you have a process that is endothermic, positive delta H, right? This is endothermic. This is exothermic. There's no such terminology for entropy. So anyway. So if you have an endothermic process, that means that this value is positive, right? And if you have a positive delta S, then this value is positive. Now, what is the sign of T? T is absolute temperature. It's always positive. There's no possibility of T being anything other than a positive value. The lowest T value is a 0, absolute 0. And there's no such possibility of attaining absolute 0. Okay? This is a theoretical number. So this is positive. So that means that this whole piece is positive. So you have a positive number from which you're subtracting a positive number. How can you make that difference negative? So you want this number to be very large, such that when it's in front of the other one, because there's a minus sign here, right? You want it to take away everything that's positive in the enthalpy. So therefore, high temperatures is what favors endothermic processes in which the system is getting disordered. Okay? So, for example, the boiling of water. Yes? As those particles are separating, they need to absorb heat, energy. Right? The process is an endothermic process. As they're separating, they're also increasing their entropy. So that can only happen spontaneously at high temperatures. If you put a pot of water on the stove, it's not going to boil spontaneously at room temperature. You need to crank up the heat for that to happen spontaneously. Once it's at the boiling point, you can walk away. It's a perfectly spontaneous process. It will evaporate or vaporize, right, at the high temperature. The exact opposite. Well, let's do it. Let's do one at a time. So everybody understands the how we dissect this to then come to the conclusion that for endothermic processes in which the system gets disordered, that happens at high temperatures. Okay? All right. So let's do the next one. What happens if you have an exothermic process in which the system is getting disordered. So this value is negative. This is positive. Here goes my pen again. This is positive. And we've already established that this is positive. So this whole thing will be positive. So from a negative number, taking away, the pen is dead again, taking away something positive, what is the effective temperature? So what are you trying to say? So will the temperature have an effect on the outcome? Will high or low make a difference? So because delta H is negative, you're taking away something positive. It doesn't matter what the temperature is, it's always going to be negative. That difference will always be negative. So that process will be spontaneous always. Always, always. So processes in which there's an exothermic heat energy is released into the surroundings, and at the same time there's a disordering of the system, then those processes will always happen spontaneously. Okay? If you go down to the bottom left, if you have a process that's endothermic, but in which the entropy is going down, this is a positive number. I don't understand why this stupid pen starts okay and then dies. Maybe I have to do this to kind of see if that works. Thank God it's not a real pen, right? So this is a positive number, right? We're talking about this scenario here, right? Endo with negative entropy. And then this entropy, the entropy is a negative number. I can't write on it. The entropy is a negative number, okay? I'm just about to scream right now, but anyway. All right, let's do it here. Delta H minus T delta S, right? This is a positive value. We're in the bottom left. This is a negative number, right? Of course, this is always positive. So this whole thing is negative. Yes? So from a positive, you subtract something negative. What's truly happening here? You're adding to it a positive number, because minus minus makes plus. So this whole thing will be positive regardless of the temperature. So those processes will never happen spontaneously. Any process that and then think about it, any process that requires absorption of energy, it needs to be provided fuel, and on top of that everything is getting ordered, that's not happening. That goes against the universe. Okay? Not happening. The last scenario would be when you have something that's exothermic, but in which the system is at the same time getting ordered, right? So if you have exothermic, this is negative, right? It's getting ordered, so this is negative. So this will be negative as well. So from something that's negative, you're subtracting something that's negative. How do you keep it negative? The only one that you can control is the temperature. So if you keep the temperature low, it makes the magnitude of this small, so it doesn't take away much from this negative. And it keeps it negative. It keeps it spontaneous. Okay? So the freezing of ice, for example, the water becomes ordered to make the solid. In doing so, it's releasing heat, because that's an exothermic process. Right? How do we know that? You put your hand behind your freezer, you feel warmth, because that's taking away all the heat that's coming out from as things are freezing. The only way you can make something freeze is if you put it in a cold environment, spontaneously, right? If I put a pot of water on right here, it's not going to freeze as I'm standing here, and generations will pass and the water will not have frozen. If I put it in the freezer, low temperature. That's a process that is exothermic, but the components are getting ordered. Low temperature makes it happen. Okay? All right. So make sure you understand these 4 scenarios, put it together with the signs. Again, because on an exam situation, you may be presented with a scenario that you need to dissect. Will high or low temperature make it happen? Will it never happen? Will it always happen, regardless of temperature? Okay? All right. So, a little bit of additional terminology. It turns out, we've already established that for the combustion of glucose, there's a disordering of the system, and it turns out that this is also highly exothermic. How do we know that this is highly exothermic? When you combust something, heat is released, right? This is true for burning oil and hydrocarbons and glucose, right? Your body generates heat. It's because you're breaking things down, technically combining them with oxygen, even though not directly. So these are exothermic processes where things get disordered. And in this case, delta H is negative, delta S is positive, so we are here. This is always spontaneous, right? We're at this point. So whenever you have a delta G that's less than 0, meaning the process is spontaneous, the process is said to be exergonic, not to be confused with exothermic, which refers to enthalpy, meaning heat being released. This is now we're talking about the net delta G, i.e. chemical energy, also known as free energy. Whenever that happens, that means that the products are more stable. That comes with the reaction, if reversible to a reasonable extent, the equilibrium constant will be large because the products are favored because they're more stable. Turns out that if you mix CO2 with water, at least at normal temperatures, it will not spontaneously make glucose and oxygen. That would be the reverse process. So then in this case, the exact opposite happens in terms of enthalpy and entropy. Whenever you have a non-spontaneous process that has a positive delta G, you can put numbers to the entropy and the enthalpy, but here we're doing it sort of qualitatively based on the number that's the reaction that's above. In that regard, the reaction is non-spontaneous. The term that is used is endergonic. So notice some similarities, X and end. X is meaning being released, ender meaning being absorbed. But again, don't confuse it with endothermic. Endothermic is delta H. That's positive. In this case, the reactants are more stable. Right? Notice that the reactants of this reaction or the products of this reaction are the reactants of the other one and vice versa. We've already said that on the top. The products are more stable, right? Because it has negative delta G based on this. Well, these are the reactants of this one. The reactants are more stable. Because the reactions are written in the opposite direction, right? So as we've said, when you change the direction, the signs of everything changes. Okay? So you can use similar graphs as we did previously when we were describing enthalpy changes, using now free energy, i.e. chemical energy content on the y-axis, and then of course reaction coordinate, meaning directions proceeding in that direction. So whenever you have products that have a lower chemical energy, i.e. Gibbs free energy content than the reactants, this is called an exergonic process. It means a negative delta G. What does that mean? Well, it means that the process is spontaneous. It means that the process proceeds from reactants to products. It means that the equilibrium constant is large, meaning greater than 1, meaning products predominate at equilibrium. All of these things mean the same thing. Okay? The exact opposite happens when you have products that have higher energy content, free energy content, than the reactants. It's the exact opposite. Delta G positive, the process is non-spontaneous as written. In fact, it's going backward from product to reactant. Therefore, it has a small equilibrium constant, meaning less than 1. The reactants will predominate at equilibrium. All of these things are synonymous, and they can be read from these graphs that we see on the top. So we now come to a critical piece of this whole discussion, and it's what is known as Hess's law. Hess's law applies to multi-step processes, which is what happens in biochemistry. as we're going to see. We're going to learn about several biochemical pathways that sustain life, and they have multiple steps. Glycolysis, for example, has 10 steps. Okay? Now, some steps may be endergonic, other steps may be exergonic. And you may ask yourself, well, if it's endergonic, meaning delta G is positive, meaning it's non-spontaneous, how does it possibly happen? Well, what does happen is, again, it may go to a small extent. Some product forms at the expense of a little bit of the reactants, but the reactants are primarily still there. But as we said, as long as some of that product forms and it's taken away in the next step, the process can continue. But the question is, what fuels these non-spontaneous processes? Well, it's the coupling, simultaneous occurrence of those non-spontaneous steps with other steps that are highly spontaneous. And then it turns out that the net effect, when you combine a non-spontaneous process with a spontaneous process, in which the spontaneous process releases more energy than what is required for the non-spontaneous process to happen, the net effect is a negative delta G, and it makes the overall process spontaneous. So Hess's law simply says that when you have multiple steps in a transformation, the net energy exchange or change for the process is the sum of all of the individual energy changes of each individual step. And as long as the totality of all the steps after you've added them up together makes you or gives you a negative delta G, the whole thing will happen spontaneously. So what we call coupled reactions are reactions that occur simultaneously or side by side or in proximity to each other, such that the exergonic process is releasing a certain amount of energy that is then driving, propelling forward the endergonic reactions that would otherwise on their own not happen spontaneously, but because you have another reaction that's providing that fuel, it can then all happen. So for example, turns out that one of the major tasks of metabolism is to produce ATP. ATP, adenosine triphosphate. You may have heard of this in previous lives. Adenosine triphosphate is the major fuel of all cells in the body. And one of the major tasks of metabolism is to produce adequate amounts of ATP in order to sustain all the functions of your cells. Well, it turns out that ATP comes from the placement of a phosphate on ADP, which is adenosine diphosphate, right? Put a phosphate and put a third phosphate on one that already has two, and you're making triphosphate. Well, it turns out that we're going to see where this number comes from a little bit later, but the net process is endergonic, right? Now, if that is coupled with the conversion of glucose to lactate through what we call anaerobic glycolysis, that process, which is the breakdown of glucose under semi-anaerobic conditions or conditions of limited oxygen availability, which is what happens when you're doing heavy-duty exercise, right? That is highly exergonic. So when these two are combined, the net reaction can be written as shown here, glucose with ADP plus phosphate making lactate plus ATP. Well, that becomes the sum of these two numbers. It's negative. So the whole thing, with the assistance of the breakdown of glucose, which is why we take carbohydrates, why we break them down, and we extract their energy, is with the goal of making ATP spontaneously. Okay, so when you combine reactions that are non-spontaneous with those that are spontaneous, then you can manage to ultimately drive those non-spontaneous essential processes. Because we can't live without ATP. But we need to do something else on the side, i.e. burn our foodstuffs to extract their energy to drive all of these processes that are non-spontaneous. And this is one of many examples we're going to look at. Everybody with me? Okay? All right. So that concludes the thermodynamics portion of the course. We're now going to dive into another important piece, which is kinetics. Kinetics deals with speed of reaction. And we're going to talk about the general principles involving kinetics. We're going to talk about catalysts in the context of laboratory chemistry, but focusing and looking forward to biological catalysts known as enzymes. So these are the learning objectives for this section. So we've been talking about spontaneous versus non-spontaneous. And whenever a reaction is spontaneous, based on delta G being negative, which is, as we've said, influenced by heat changes and exchanges plus order versus disorder plus temperature, whenever a reaction is spontaneous, it is said to be thermodynamically favorable. Okay? Now, it turns out that whether a reaction is favorable or not thermodynamically, meaning whether the products are more stable than the reactants and the reaction tends to naturally, spontaneously proceed in that direction, has nothing to do with how fast it's going to go. Okay? So, explosions are exceedingly fast processes, right? They happen before you even have known that they're done, right? Whoop, beep, done, explosion, gone, right? Highly spontaneous reactions once they're triggered properly. We all know that the rusting of metals is a spontaneous process. If you take a piece of iron or zinc or whatever, leave it out, it's going to rust. But is it instantaneous? It is not. It can take weeks, months, years even for certain things to spontaneously rust. So this is an exceedingly fast reaction. This is an exceedingly slow reaction. Okay? For example, diamond. What's diamond? What is diamond? What is made of? It's pure elemental carbon, right? Pure elemental carbon. Where does diamond form? It's because of that, yes, right? Where in planet Earth? Does it grow on trees? Do we pull it from trees? No, we do not. Where is it? Caves and places, godforsaken places underground, whereas if you've seen the movie Blood Diamond, you realize the tragedy of diamonds. It's tragic. But because of the exceedingly high temperatures and pressures that happen under these underground mines, graphite ultimately becomes diamond under those particular conditions. Of course, when we find the diamonds and harvest them and bring them out and make them pretty, they're now spontaneously reconverting back to graphite. In every piece of jewelry that contains pure diamond, it is, as you speak, as you sit here, spontaneously becoming graphite. It's not going to happen in your lifetime, probably 2 lifetimes, probably 3 or 4 lifetimes. Eventually it will, but it's a super slow process at normal atmospheric temperature and pressure. Because under the conditions that are happening underground, the spontaneous process is the opposite. Graphite becoming diamond. When you bring it out, the opposite is what's spontaneous. But it's so slow that you'll never be able to perceive it. So this is the whole point. Spontaneity has nothing to do with rate. Okay? Both of these processes are spontaneous. This is a very low rate. This is a very high rate. So it turns out that for a process, chemical transformation, to happen at an appreciable rate, one that you can observe and measure as you wait, as opposed to having to wait a lifetime for it to happen, there is a minimum amount of energy that must be exchanged between the reactant particles. If that amount of energy is not provided, or it cannot be absorbed, or it cannot be exchanged, there's no reaction. Okay? Until you get to that point. That energy is known as the activation energy, abbreviated capital E with a subscript little a. Now, the activation energy is what actually initiates the bond-breaking process amongst the reactants. So until that energy is exchanged, nothing can technically be taken off. That's what sets it off. Nothing can take off until that energy is provided somehow, right? So you can use little cartoons to make it sort of more easy to understand. You have your reactants up here. There's an energy barrier that needs to be overcome. Until that barrier is overcome, which is that activation energy, nothing will happen. Once it is overcome, then it's downhill from there. The products can proceed, right? Now, every reaction has a unique activation energy. You can measure it, it turns out. And it depends on these factors that are shown here primarily. So the number and types of bonds that need to be broken in the reactants and then formed in the products. So when things are reacting and atoms are being reorganized as the process is taking place, certain bonds need to be broken in the reactants, new bonds need to be made in the products. So the combination of all of that, remember, breaking bonds requires energy, making bonds releases energy. All of these processes, there's energy changes and exchanges, and all of that contributes to the activation energy. And of course, with that comes structural changes that must take place in the reactants in order for them to ultimately be able to make products. So if a reaction is really fast, that means that the barrier is really low. Okay? So low activation energies means that it doesn't take much to get that going. So that's going to ultimately be a fast reaction. However, if this is a very high barrier, you have a tall wall over here, right? It's going to take a lot more work, a lot more energy for you to be able to get over that hump, that barrier, right? So that means that it's going to make the process slower. So slow processes have high activation energies, and as we've said, fast processes have low activation energies. Now, the only way reactions can happen is if and when the reacting particles interact with each other. First of all, they need to be interacting with each other. But they need to do so at sufficient speed such that when they collide, they must collide. They then exchange enough energy with each other to then technically have exchanged the activation energy, so that sets off the whole process. But it's not just merely a collision. The collision needs to happen in the proper orientation. Because if they're not coming together or touching each other in the right way, doesn't matter how fast they're going, if the portion of one that needs to interact with the portion of the other, they're not ultimately interacting, then nothing's happening. Right? Doesn't matter how fast they're going. So there's two things. They must collide at the right energy for them to be able to exchange that activation energy, and they must interact in the right three-dimensional orientation, one relative to each other. So because the entire premise of fast versus slow involves collisions between particles, this forms the basis of what we call the collision theory of chemical kinetics, which in fact falls within the larger umbrella of what we call the kinetic molecular theory of matter, which simply explains how matter behaves. In any sample of matter, particles are constantly moving and they're constantly interacting with each other, they're colliding with each other for the most part, unless they're super solid, right? Even in solids, particles are vibrating, they're interacting with each other. But then when we speak of chemical kinetics, there's sort of a subset of those interactions. They will ultimately lead to chemical changes, right? Depending on how things are coming together. So the temperature of any sample of anything, temperature in general, is a measure of the average kinetic energy of the particles in that sample of whatever it is, right? So as we've said, matter is composed of particles that are moving at random they have an average kinetic energy based on the temperature that they exist in. Now, what happens if you increase the temperature? The particles start moving faster, whether they're vibrating or moving from point A to point B. So ultimately, as you increase the temperature, particles are moving faster, and two things result from that. When they collide, they will collide with greater force because they're moving faster. And that also increases the probability that they're going to collide. So those two things combined are ultimately what leads to a chemical transformation. Okay? So, as everybody knows, if you're going down 93, right, you're more likely to get into an accident if you're going at 100 miles per hour versus if you're going at 55 miles per hour, right? Because that's more speed, more chances of things happening. So this is what I was talking about with the concept of orientation. So here you have NO molecules interacting with O3. Ultimately, the products are NO2 plus O2. So for the process to be effective, the oxygen of NO, the oxygen is typically represented by red, nitrogen, and blue. The oxygen of NO needs to collide with one of the oxygens of the ozone so that one of those oxygen atoms in ozone gets transferred over to then form NO2, right? But it needs to happen not on the, sorry, I said on the oxygen. It needs to happen on the nitrogen. The nitrogen is the one that needs to pick up that additional oxygen. Because if you draw a Lewis structure of NO2, nitrogen's in the middle, the two oxygens are on the sides. So they're doing with little models, right? So if what happens to collide is the oxygen of the NO2 with, let's say, the middle oxygen of ozone, well, they can come together as fast as they want, but nothing's happening because that's not the right orientation. And even if it's the nitrogen of the NO, which is blue, that's colliding with O3, if it's colliding and touching the middle O3, the middle oxygen of the O3, again, not happening. Because what needs to happen is that one of the end oxygens, they're the same, either that one or that one. As long as one of those collides and touches the nitrogen of the NO, this is the interaction that needs to happen. Now, that needs to happen, but it also needs to happen at the right speed, right? So if those two things are met, then there's reaction. But if they don't come together with enough energy, nothing's happening, no matter what. But even if they come together with the proper energy or speed, which is a measure of their energy, if they're not touching in the right places, then nothing's happening. So both of those things need to happen simultaneously. So activation energy, which you can also write it depending on what book you read, and let me make that bigger because you're not, let me see if the pen is working. Delta G double dagger. So like a little double dagger. That's what this is. It's another abbreviation for activation energy. Okay? That's the energy that must be exchanged between the reactants that are colliding, the particles that are reacting. When they collide, they must exchange that amount of energy in order to start the whole process and start the bond-breaking, bond-making process. So as we've said, that exchange is more likely when the particles have higher kinetic energy. Why? Again, the particles are moving faster. There's greater probability that they collide, but they're also more frequent, okay? Because if you're going faster, there's more probability. There's an increase in the number of collisions. And if you increase the number of collisions, then the percentage of collisions that will be productive goes up because there's more collisions, right? So therefore, greater temperature gives greater kinetic energy, which provides for faster motion, greater probability of collisions, and it makes more frequent collisions. Therefore, the percentage of those that are productive also increases. Okay? Now, we also have to take into account the numbers of the particles that are present in your reaction. So not only does temperature increase probabilities and frequencies of productive collisions, concentration is huge. Because if you have more particles, then again, there's a greater probability of them colliding. And if you increase the probability of collisions, the percentage of those that will ultimately be productive also increases. So again, back to my little analogy, which is not very pretty, but that's what I can come up with. If you're going down 93 on a Sunday morning at 6 a.m., you can probably get away with going 100 miles an hour and not get into trouble, right? In terms of, well, never mind the popo, it's just the going down there's nobody there, right? But if you're going down 93 at 100 miles an hour at 7 a.m. on a Monday, nope, you're going to get into an accident for sure. You're going to have a collision because there's too many things surrounding you, right? So of course, when you want thinking about a reaction, the more particles, the more collisions there are going to be, the better it is for the outcome, right? So concentration and temperature are the two critical things that will lead to higher rate. The temperature because of the energy considerations of the speed of the particles, the frequency of the collisions associated with that. Concentration will be just because there's more of them, right? There's more of them. So let's look at this very generic process up here. Some random reactants, A, B, and C, making products, whatever they may be, each one associated with their stoichiometric coefficients. So it turns out that you can go into the laboratory, which we're not doing in this course. We're not doing a kinetics experiment. They're fun, semi-fun to do because you're collecting a lot of data. But anyway, you can go into the laboratory and study chemical reactions and take samples over time and measure. So you put everything together, take a sample at time 0 so that you know what you have before anything has happened. Then at certain time intervals, let's say every 10 minutes, you take another sample and you analyze what's in there. You do 20 minutes, another sample, analyze what's in there. And you do that for however long you need to be able to do that. And then you can observe, you can measure using instrumentation these days, obviously, how much is left of A, B, or C at this time and that time and that time and that time. And that allows you to then establish how does the rate of reaction change over time and how is that dependent on the concentrations of the different substances. Okay? So for every reaction, you can come up with what we call a rate law. That is simply a mathematical relationship between rate and the concentrations of the different substances involved in the reaction. And of course, we have a proportionality constant that we call the rate constant. And it turns out that these rate laws, which must be experimentally determined, there's no other way to figure out the rate law of a reaction other than going into the lab and studying what happens over time. It takes the form of rate equals some proportionality constant called the rate constant times the concentration of the first substance elevated to some exponent. Same thing with B elevated to some other exponent, C to some other exponent. Now the point here, the reason why we use different letters, notice the stoichiometric coefficient of this one is little a, this exponent is W. This is little b, this is x, this is little c, this is y. It's because there's no relationship whatsoever between the stoichiometric coefficients of the substances in the balanced reaction and their contribution in terms of exponent value in the rate law of that same reaction. This is why you cannot predict anything. You have to go into the lab and do the experiment and figure out how does this reaction depend on A, B, or C, regardless of its participation in the net reaction. So these exponents are referred to individually as the order of each reactant in the reaction. So the way that we say this, we say that W is the order of A. So A has order W, B has order X, C has order Y. the sum of the exponents of all of the substances involved, in this case WXY, the sum of all that number that you get, is what we call the overall order, or simply the order of the reaction as a whole. Okay? The reason we mention this, because you're going to be doing experiments later involving enzyme kinetics, and you're going to be speaking of zero order versus first order versus this order versus that order. You need to know what that terminology is referring to. So, what turns out to happen is that these values, W, X, and Y, are actually a reflection of how many of those particles of that substance are actively participating in the step of the reaction that is the slowest step of the process, which is what we call the rate determining step. If any substance in the reaction, even though it may appear as one of the reactants, but if that slowest step of the process, any of the substances do not actively participate in that step, meaning they may participate before or after that step, but not at the step that ultimately is the bottleneck that determines the rate, then their order will be zero. They don't appear in the rate law. Okay? So these values of W, X, and Y can only be determined experimentally. As I've said, they have no relationship with the A, B, and C of the stoichiometric coefficient, and the value of K, of the rate constant, must also be determined experimentally. Okay? Now, when the order of a reactant is zero, if you elevate anything to the power of zero, what happens? What do you get? You get 1. The answer is 1, right? So what that truly means is then, if the order of anything here is elevated to the 0, it becomes 1, meaning it does not contribute to the rate. So you can add boatloads, you can add more or less, it's not going to have any effect, because it does not affect the rate. Only substances whose orders are 1 or greater will be affected by changing their concentration, because the rate is dependent on their concentration. If the order is 0, the rate is independent of that concentration. What does that mean? That that substance participates in the reaction either before or after the rate determining step, and therefore its presence, its concentration obviously cannot be 0, but whether you have more or you have less, it's not going to have an effect on the overall rate of the reaction. So when you're writing these energy diagrams, you have to be mindful that these graphs that we've been talking about up to this point, these are a little bit different, but the concept is exactly the same. They have actually 2 regions to them. So we've been talking about, let's say, reactant A becoming reactant B, and we've talked about delta G, right? This is exergonic. Products are more stable than reactants. This is a spontaneous process that has whatever value of delta G. What we hadn't talked about up to this point is this little hump, right? Well, this hump, in fact, represents the activation energy of the reaction. That's the kinetics portion of the process. So here we have 2 reactions with the same exact delta G, so they're equally spontaneous. Meaning if you start with the exact same concentrations of A and C, they're, at the end, once equilibrium has been reached, you're going to end up with the exact same concentrations of B and D, because they have the same exact delta G. However, which one of these 2 is the slower reaction? C to D, because the activation energy is higher. So, let me see if this works. No, it doesn't work. All right, it's attempting to, but it doesn't work. So anyway, I can't reach it because I'm short. But so if you measure the height of that, it's lower, smaller than the height of that one, right? So the activation energy, notice it's a little bit shaded here, is higher for this one. This is a slower process. This is a faster process. So if you wait long enough, the concentration of B and D will be the same because they both have the same delta G. But this is going to take much longer to get to that point because it's a slower process. So if you're taking samples from both reactions to try to establish what the rate law is, you're going to observe that the concentration of B appears faster on this one. Concentration of A goes down faster on the left. Concentration of D appears much more slowly. Concentration of C disappears much more slowly as well because this is a slower process. But ultimately, they're both going to have the same outcome. You can also have reactions that have the same activation energy, but then they have different delta G. So what is the difference in the outcome of these two? So the rate of disappearance of A will be the same as the rate of disappearance of C because they go at the same speed. However, the difference between B and A is smaller than the difference between D and G. So what that means is that at equilibrium, there's going to be more B than there is D. There's going to be more D than there is B, right? Because this is lower energy. So D is more stable than B. So even if you start with the same concentrations of A and C, at equilibrium, there's going to be less C than there is A, and there's going to be more D than there is B. Because of the delta G difference, which is what determines how much product versus reactant exists at equilibrium, for this one, that number is much more negative. So the difference between these two reactions, they're about the same speed. The one on the right has a larger equilibrium constant. That's how you technically should be looking at it, because there's more product in the reaction on the right than there is on the reaction on the left. Okay? You could technically say the one on the D has a greater degree of spontaneity, more spontaneous than the one on the left, right? So more D than B, larger equilibrium constant for for the right reaction versus the left reaction, even though they happen at the same speed. So this is simply trying to illustrate putting it together. So the thermodynamics of the reaction are down under the hump when you compare the relative Gibbs free energy of reactants versus products. The one on the left is an endergonic reaction. The one on the right is an exergonic reaction. So the equilibrium constant for the one on the right is greater than 1. The one on the left is less than 1. The one on the right, more products at equilibrium than reactants. The one on the left, more reactants than products at equilibrium. It has nothing to do with the top hump, which is speed. When you look at the hump, at the height of the humps, just by quick inspection, it seems to me very subtly that maybe the one on the left is a little bit higher. Could be an optical illusion. Notice it has nothing to do with the other discussion, right? So the kinetics of the reaction is here, right? Depending on how high this is relative to the reactants, right? Relative to the reactants. Whichever has the higher hump, higher activation energy, that's the slower of the reactions. There's nothing to do with spontaneity or relative stability. So we started our discussion, rate has nothing to do with spontaneity, right? This is a reaction that it is spontaneous. This one is not spontaneous. But its rate is determined by the height of this. It has nothing to do with relative stability of product and reactants. Okay? All right. So when we're speaking of reactions that have multiple steps, then we need to distinguish different positions along these reaction energy diagrams that we're sort of talking about here. And we need to distinguish between what are known as intermediates versus transition states. So an intermediate in a reaction is a highly unstable because it has a lot of chemical energy, i.e. Gibbs free energy. It's very high relative to the reactants. But it is structurally complete, meaning bonds are fully formed, Any bonds that had been broken relative to the original compounds have been fully broken. Any new bonds are fully formed. But because they're so high energy and unstable, they don't last for long. They're very swiftly consumed, and they proceed to the next step, and to the next step if there's multiple, right? Until eventually products are produced. I'm going to show you a graph in a moment. Let me go forward. So these are our reactants. This is an endergonic reaction. Notice it's slightly positive. So we go up to our activation energy barrier up here, and then here's the first intermediate, right? Higher energy than this, but it's what we call a local minimum along the graph. So here's a minimum, here's a minimum, here's a minimum. They're sort of valleys, right? Valleys at the bottom. Kind of like the reactants in the process, but they're neither. They're in between the process. Now, the second one that we need to talk about is what are known as transition states. These are also high energy and unstable, but as the term implies, these are the structures that are in transition. They are in the process of having their bonds broken and having the new bonds formed. So everything's sort of in the middle, in between. It's actually in the process of actively transitioning from one thing to the next. These are the highest energy species along the path of a reaction. They represent the maximum, the mountaintops. So even for a single step, this is the transition state up here, right? When that activation energy has been ultimately absorbed, we said that that's when bonds start breaking and things start happening. Well, that's the transition state. So if it's a single step, it's just the highest point along the path, which is the hump, right? But you can also speak of in a multi-step process, this one has one step. This is the first transition state number 1. Then bonds form, and you get an intermediate. That intermediate doesn't last for long. It further reacts. It has its own activation energy, reaches the second transition state, which then new bonds are being broken, things are happening. Up here, it reaches a second intermediate. That is even less stable than the first one because it's higher energy. That one continues to react through the third step, high energy, comes down, forms a third intermediate, and then we reach the highest point in the reaction. This is what we call the rate determining transition state. This is the highest energy position along the entire reaction. If you compare the energy of this point with the reactants, this is the highest one. This is the rate determining step. So this reaction has 4 steps. 1, 2, 3, 4. Every peak is a step. And the highest one relative to the reactants is the one that ultimately determines the rate. We call that one the rate determining step. In this case, it's the last step. So only the species that are present and participating here are the ones that ultimately determine the rate law and the rate of the reaction. So then at that point, it just falls to the products. The net result down here is exergonic. This is the thermodynamics. All of the kinetics is up here, right? How fast it's going to go. The first step is not too fast, but it's the slowest of all, is the last one. Steps 2 and 3 are pretty quick because very small activation energy. Okay, so for example, how many steps in this reaction? There's only one step, and this is the only transition state, right? Here's a reaction that has how many steps? 2 steps. It has 1 intermediate and 2 steps. There's always going to be 1 less intermediate than there are steps. So if it's only 1 step, there's no intermediate. It just goes directly from reactants to products, right? Now, the rate determining step is which step? The first or the second? The first one, right? Because that's the one that highest activation energy. Here's a 2-step process in which the second step is the slowest. Okay? All of them are exergonic. Notice, products have low energy than reactants. It has nothing to do with what's going on up here, right? Equilibrium constant greater than 1. Spontaneous process. Not by much, but these are 3-step reactions. Here one in which you have rate determining step is the first step. You have 2 intermediates because there's 3 steps, right? The conversion of intermediate 1 to intermediate 2 is relatively quick. Notice a very small activation energy. And then from the second one to the last one, moves up a little bit, and then here's the products. The rate determining step is the first step. Here's one in which the rate determining step is the second step, right? This is the first intermediate over here. First transition state up here, first intermediate. Here's the second transition state, which is the rate determining transition state. Second intermediate, another transition state, and it happens. So again, so that you can sort of visualize, you start with something. Something happens, and then it forms this thing. Something happens to that, and then something else forms. Something happens to that, and then you get the final product. Okay? And that can happen once, twice, 3 times, however things. And at each point, each intermediate is different than the other one. It has a different structure. Something has happened. First step is the slowest. Second step is the slowest. The last step is the slowest. Okay? So here's one. So which of these represents a fast reaction in which the reactants are favored over products at equilibrium? So fast and endergonic. Okay? So, the answer is, so for it to be fast, what needs to happen? There has to be a small activation energy. So C and D are out. They have a large activation energy relative to the other 2. For reactants to be favored at equilibrium, the relative positions need to be how? Reactants on the left. So you need to have products at a higher energy, right? So the answer is B. So A is a fast reaction in which the products are favored. That's the best reaction you can ever want because it's fast and it favors products. The worst one is D. Slow and reactants still remain. That's the worst situation. All right, we will continue, and we only have like 4 slides left, so we're going to wrap this up next week.
I did get the clicker, but I emailed the troubleshoot comment, and I was like, because I couldn't get onto the class today.
Okay.
And they said that maybe I'm not an active student under the class list.
No, I mean, connecting to the class has nothing to do with your registration process. You just need to be on the right channel, which you are. So were you able to click at all?
No, it wouldn't let me.
Really? That should.
It says I'm not enrolled in the course.
This said?